if we have to define general principles of design in biology and also as guidelines for designs in bioengineering, symmetry is one of the central ones. Okay? Symmetry is something that we see all around us, but we also see fundamental asymmetries. Take the brain, the most complex object we know in the universe. It's kind of symmetric in a way, not completely. Anatomically, you see differences, but in terms of functionality, it displays remarkable asymmetries, right? We know there are these left-handed people, right-handed people. The majority of people is right-handed. Why? And also, and we'll go to that at the end, functions such as language are clearly lateralized, right? Right-handed people have language functions. It's not like language is here, but some parts of the language functions are in this side, not on the other side. Why is this asymmetry there, right? What's the origins of asymmetries? What are they meaning? One of the most clear examples of asymmetries we also see in biology has to do with molecules, right? I made this simple diagram here. Took the amino acid alanine and is image in a mirror, right? We find both kind of shapes in nature, right? If you look at in chemistry, so I can generate these, I can generate this. They cannot be exchanged to each other, right? As it happens with the right hand and the left hand, right? They are symmetric in a mirror, but I cannot replace the one by the other. Two different kinds of possibilities. But in biology, I don't find both. They exist in the chemistry, but biology has made a selection, right? A choice, if you want. We have a given handedness in nucleotides, in the nucleic acids, right? They are kind of D-handed, whereas in proteins they are left-handed. Why that particular choice? Okay, it's of course there's a number of arguments you can make in terms of saying functionality, for example. If enzymes had to do with two kinds of the same thing in different symmetries, it would be really difficult to do anything, right? You should solve two kinds of forms. But nevertheless, what is the origin of that? What happened here that only one of the solutions was there? Is one better than the other? We can get inspiration from technology to rethink about these ideas, okay? I put here this example, the clock, the standard clock. Why is this, we say, clockwise? Why it turns in this particular direction, right? You could say, you can argue that maybe the people who invented the first clocks, they kind of get inspiration or intuition or just biased by sun clocks, right? But the reality is that might have happened, right? But if you go, for example, to Florence and you see the clock at the cathedral, the Paolo Uccello clock is anti-clockwise, right? At some point, hundreds of years ago, that decision was not made, and it makes sense because there's no reason why this is better than this. They are totally equivalent, right? Actually, as I'll try to show you, if we were able to use a time machine to go to the past and introduce in the market some counterclockwise clocks, we might have changed that particular story in history, right? What other examples are there from technology, okay? One that is pretty nice and illustrative is what happened with the video recorders, right? There was a time, once upon a time, there were two competing kinds of designs, VHS and Betamax, right? If you look at the historical record or how many of these machines were in the market, how often they were used, you will find the following. They were really close to each other for a while, right? That would be, for example, VHS, okay? and that would be beta max. Let's put it beta, right? Very close. The reason is that people was just starting to use this technology. They both designs were pretty similar. Beta was supposed to be more advantageous in terms of quality and storage. But what happened was, eventually, beta keep going, whereas, sorry, BHS keep going, whereas beta decayed into extinction, okay? So we could say that both designs were pretty much symmetric for a while, right? But something happened. Something made a decision that was against what actually the experts were saying. You will say the optimalist beta should win. Why that happened? Well, this is a general problem that is relevant for our discussion about bioengineering and also about evolution. Because one of the things I'm going to show you is that by trying to understand the origins of broken symmetries, choices between two equal configurations, we can actually introduce historical dynamics, right, into the mathematical description of our systems. How can we do it? Let me take as an example this system, right, which is might seem not the best approach to considering biological systems, but it actually is. Imagine that I consider the following. Imagine I have a population, right, with consumers that can use one of the two designs, right? So let's call X1 the first population and X2 the second population, right? Okay, I'm going to assume, again, simple assumptions. Everybody is here. I consider all the possible consumers are going to use one or the other design. So I'm assuming that everyone is having video recorders, right? Suppose this is BHS, and this is for beta, okay? If people is using one or the other, right, I can think in terms of competition. Remember that, and we'll go back to that, right? We can actually make competition explicit with a given function that I can find out. The thing is that the microscopic dynamics is as follows, right? Imagine I'm someone that is using beta, okay? Of course, in the market, one important thing is compatibility. If I know a lot of people who is using beta, that's good for me because I'm going to exchange things with them. If a lot of people around me is using BHS, I might be likely to change, right? Because, you know, it's more people using that, is less opportunities to actually exchange anything with them, okay? So in other words, the idea is that the part of the dynamics that we need to include here is how likely is that I go into the other possibility, right? Change or remain in my current state, right? So there's something here that connects these and these, right? And I need to describe in a way whether or not transitions happen, right? I put this direction here, but actually it's the flow in any direction. And I can do that considering that it should be some kind of function here and here that I should find out, right? That tells how likely is that I move in one direction or the other, right? Changing my decision about whether I use this or this, right? So we'll formulate the simplest model that we can, okay? And we'll do it as follows. Two differential equations for x1 and for x2, okay? As usual, since we have to assume that there are parameters that in a way say how easy is something to happen, okay? I'm going to include some parameter that says how rapid is the dynamics, let's say mu. And I'm going to use the same in both equations, okay? I don't have to, but let's make the same. This, of course, is coarse-graining a lot of things. You know, how is the economy? How easy is it that people makes actually this change easily or not? In any case, we know that wherever it happens to the amount of people in each state, right, it has to be population dependent, right? Now, I should find out who is this, again, using the simple intuition that I can formulate, and remember that I have a constraint here, which is that I'm assuming that everyone is participating in that. In the simplest case scenario, as usual, I'm going to assume that the overall amount of population is constant, and for me, the simplest thing to do is consider this is normalized, as we did before for the competition problem. And I now to have is to formulate this properly, okay? Everything here actually is to be defined in these terms, right? But let's think in our intuition, okay? If I am in a group with few people in a given state, right? Say beta. The vast majority in BHS is very likely that I'm really going to move, right? It's no point to keep being part of beta. If both are similar, right, I should be in a state where I might not do anything, because what is the advantage of changing if half and half are in each state, right? What is if I am in the majority, right, if I am in the group that is dominating and it's just few people here, I'm not going to move, right? I'm going to change. So one way of doing that is to use a simple diffusion approximation. It's a flow here. So let's write this. The choice we made is, it just depends on the difference, right? Think about it. I have a growth that depends on how many individuals I have in the population, but this could be positive or negative depending on the balance between the two populations. So the balance is explicit here. If I'm the majority, so more BHS people than beta, this is positive. So my population here in this compartment will keep growing. If it was the other way around, if beta was larger than me, okay, then I'm more likely to abandon this decision, right? This particular choice. So that would be negative. And the larger the difference, the more likely is that to happen. That's exactly what we wanted to include in the system, okay? So if we consider this, of course, the second function will be just the complementary form, working exactly the same way, okay? And we can just take one of these equations. Remember that since we have this constraint, it's only one single variable problem. Take, for example, the first equation, right? Knowing that from the constant population constraint that my phi function here is just the sum of these two terms in this part, okay? So if we do it, for example, for x1, we will have mu x1. This is what I have to introduce now, right? Minus x1, okay? And my phi function will be this plus this, so mu x1, no, assuming this form, plus mu x2, all right? Assuming this, right? Okay. Actually, I can make it nicer because this is just a difference of sign here, and that will be just mu x1 minus x2, right? That will be a minus sign, and actually this is just this, right? That's my phi function. Okay. So if I write down this, okay, this is what is phi here. Okay, now I just need to manipulate these expressions to make it a nice result. knowing that I can use this. All right. So as an exercise for you, you do it, okay? And this differential equation, all right, turns out to be written in a compact form as follows. If I'm not wrong, it's going to be 2x1 mu 1 minus x1 and 2x1 minus 1. All right? Okay. So this is a result that kind of resembles something we saw when we studied the problem of cooperation. Okay? I'm saying that it kind of seems, but there's actually a almost identical form, but something is reversed here in terms of the signs. Okay? So if we analyze this system numerically, so we integrate this, you can do it actually analytically, numerically, but you will see the following, right? If this is time and this is the actual values of x1, for example, right? You can actually see that the fixed points, the equilibrium point of here, are very clear. One is extinction. There's no one there. A second one is total dominance, right? That comes from here, right? I won and everyone is using that. And there's a third one, which is 1/2, right? Half of people is using one, half of people is using the second. If I solve this numerically, right, what I will find out is that this is 1/2, 1, 0, okay? If I start in a population level that is higher than the average, so it's a bit majority, even a small majority of people using this design, this goes into full dominance, okay? If I take other quantities, right, this moves wherever it goes, okay? Whereas if I start from an initial condition where I'm in the minority, right, the behavior is precisely the opposite. I go into extinction, right? Okay, so that would be x1, 0 less than 1/2. It will be x1, 0 larger than 1/2, okay? If you do the stability analysis, you can do it easily, right? You will find out the following, and that's a really nice result. These 2 points, both of them are stable. Okay? So there's 2 possibilities of ending up in my dynamics, whereas this one is unstable. If you remember, it's right the opposite what we find out when you analyze the problem of cooperation. So how can I interpret this in terms of a potential function, and what are the consequences? All right, so from this expression, that's the function I use to write in this way, in 1 dimension, right? I can find out the potential function that for this particular system is quite illuminating in terms of how the dynamics works, right? And why you can say that history is included into the problem, okay? Remember that you can calculate the potential function is a straightforward calculation because this is just a polynomial, right? And for this particular system, you can show that the potential function looks like this. This is mu 1/2. You can see this is a cubic system, so the potential function is quartic, plus this. This is the result. Let me say 1, 1, okay? How does it look like? Remember, in cooperation, the potential function was something that had a single valley, right, and two hilltops. Here is the other way around, right? My function here is like this, okay? If this is my x1 variable, of course, if I use x2, it will be totally symmetric, okay? This is 1/2, right? The state where we will be coexisting, whereas here and here, absolutely symmetric, you have the two final potential solutions that are stable. One is I lose, the other is I dominate, okay? Here will be with the analogy of the marble, my marble in the top, that it can only roll down either here or here. And that's the whole point. Where do you go? You have a completely symmetric system, identical parameters, everything is totally equal. Imagine I start in the same conditions. Any small fluctuation that drives you either here or here will be inevitably amplified in time, right? So that you break the symmetry. We talk about symmetry breaking because this situation, when you have two symmetric choices, is broken in favor of one of them. So this is something that happens repeatedly in many different circumstances, okay? One important message in terms of design principles is that because of this phenomenon that has happened again and again, in particular in technology, but also in biological evolution, this amplification phenomenon leads into a state that might not be the optimal, okay? The optimal state doesn't need to be the one that has been chosen. Amplification phenomena, the nonlinearities that are involved in this kind of dynamics, dominate and make the choice, right? This has happened repeatedly in evolution, as I was saying. In some cases, this symmetry, this so straightforward symmetry, is not as clear, right? But these amplification phenomena have happened, right? A great example that you have and you use every single day is the keyboard. The keyboard has a particular structure. The keyboard that we use every day is QWERTY, right? Why QWERTY, right? The English keyboard is typically like this, with maybe one key variation, depending on what country you are. But this is a rather universal thing, right? What is the origin of that? Our intuition will say, well, this is probably the most optimal keyboard able to access every letter the quickest possible, right? But it's actually not true. Originally, QWERTY comes from the old typewriters, actually something that got extinct, right? A kind of technology that just disappeared. But the keyboard inherits that. And the original typewriters had a little problem when the guy, Scholz, who designed them, tried to make them fast. There was a mechanical problem, right? The little keys typing in the paper were easily stacked to each other. So he decided to do a decision which was, let's place some of the letters in strange places so the keyboard is lower. But what happened with that is that, not being the optimal, it got advantage in the market. And the more advantage it got, the more quickly it expanded, right? So we have a suboptimal design that is just an amplification phenomenon that comes from nonlinearities. What else is there? Why symmetry breaking is important beyond these examples? Well, symmetry breaking is a process that happens repeatedly in our organism when the embryo develops, right? From a single cell, remember that from a single cell we construct everything. And this everything contains many asymmetries. Where do these asymmetries come from? from mechanisms that might be more sophisticated than this, but essentially allow non-symmetric states to emerge, which allows complex information, complex heterogeneity, etc., etc. In the brain, we have this problem of understanding what is the origin of asymmetries. But even dynamically, there are phenomena that clearly indicate that this happens here, that symmetry breaking happens in a dynamical way. And the simplest example of that has been analyzed in the lab is the Necker cube, right? This simple cube that you can draw, right? And if I ask you what is the front face here, there are two choices, right? Either you see this face as the front one, okay? Or you see the alternative, right? That's what the brain tries to see as the face here. So I have two symmetric states. No one is better than the other. And what has been found from neurophysiological studies and magnetic resonance studies is that this kind of potential is there, that the brain dynamically can now shift from one side to the other, right? In one side, I see this face, right? But if I wait, the brain will shift and see this state, right? Why? Because we have an attention mechanism that can easily shift between the two potential symmetric situations, right? In this case, I can jump from one side to the other because the system is not totally fixed, but you have dynamical behaviors, right? And there's a long list of examples that we can formulate. This particular formulation of the symmetry breaking problem can be reconsidered, for example, to actually address what I was mentioning at the beginning, the asymmetry in the chemical world, right? You can find models that try actually to answer that question. And the suggestion is that at the beginning, before life dominated the planet, right, we had a chemistry with both configurations, right? But life chose one of them. Everything evolved in one direction. Which one was the best? None of it, right? Life needed to choose between one of the two possibilities and probably did it, right? And what we see today is what in the literature is known as a frozen accident. Okay? Because it was strongly dependent on original fluctuations, so it's accidental in this sense, but the final outcome, it's frozen. It cannot be changed. It's just stuck in the system, okay? All right, you can actually go into different potential ways of looking at how this can happen. One that you can actually do as a simple exercise is the following. Assume that you have a system with two kinds of objects, right? And that these objects replicate, right, by finding each other, let's put it this way, right? Every time two of them stuck together, they create another one, right? Let's say that with a given rate. And assume that there's another species that also do the same, okay? Independently, but they have to find out the other, okay, in every case. So you can actually show that you can formulate that in a dynamical form, right? Find out an equation that you will see is not different from this one, right? And from that, you can actually do a number of things. For example, a very nice one is to make a simulation model, right, with space, for example, and see that if this is time, imagine that you start from an initial configuration where A and B are more or less the same, right? So this is A. No, this is to make something simpler. Suppose I take population A minus population B, and this will be 0. So at the beginning I'm here, more or less. And since this, if you implement that with random rules and everyone can find another one with some stochasticity, you'll see that the system performs this way. Okay? It either goes into a state where A dominates, right? That will be the positive part, or a state where the other way around, okay? Where B dominates. That will be, again, the symmetry breaking process, okay? And that's a very general phenomenon, so general, in fact, that physicists have been exploring this in the context of why in the universe we see some particular things like matter instead of antimatter. We can generate antimatter in the lab, but why do we observe that particular configuration in our universe and not the other? Okay? These kind of problems have also been addressed by scientists in very different scenarios, as you can see, right, from history to the origins of the universe. And so that's why we can say that there's a handedness in the universe. And as a final point to be made, one important thing that you should explore also is the asymmetries that we have in our bodies, right? Again, design principles. The heart, for example, contains an intrinsic asymmetry. Where does it come from? Can I use this kind of picture, or do I have to go into other kinds of mechanisms? As you can see, whether or not nature is able to generate asymmetries is at the core of generating complexity in biology and elsewhere.